So this is 5.3, Objective 2. So the last thing that we talked about in Objective 1 was the probability that if you toss a coin, that you get a heads on both flips. And we had written out the sample space. So we had heads, 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 tails, tails, heads, and heads, heads. Tails, tails. Sorry, that one should be tails, tails. And then we said that the probability of your event tails, tails was 1 out of a total of 4 different outcomes. Those are independent events. What you toss on one coin has no effect on what you get on the second toss. So when you have independent events, you can multiply the two probabilities together. So the multiplication rule for independent events says that if E and F are independent events, then the probability of E and F equals the probability of E times the probability of F. So going back to our coin example, the probability that you get a head on the first toss is 1/2. The probability that you get a head on the second toss is 1/2. Sorry, it was tails, tails. It's the same probability. So when you multiply 1/2 times 1/2, you once again get that 1/4 that we had gotten when we had written out the sample space. So if you have independent events, so if you're using the word and for two events, the probability of heads and heads, you multiply the two probabilities together. So the probability that a randomly selected female aged 60 years old will survive the year is 99.186% according to the National Vital Statistics Report. What is the probability that 2 randomly selected 60-year-old females will survive the year? So again, we had talked about this in the last video. The probability that one woman survives in no way, shape, or form affects another woman living or dying. So those are independent events. So all we're going to do is multiply those two probabilities together. So the survival of the first female is independent of the survival of the second female. We also have that the probability that you'll survive is 0.99186. Again, just change that to a decimal by moving the decimal point 2 places to the left up here from your probability, your percent, sorry. So the probability that the first survives and the probability that the second survives is going to equal the probability that the first survives times the probability that the second survives. So they both have the same probability, so that's why we're multiplying that 0.99186 by itself twice. So probability the first one survives, the probability the second one survives, multiply them together, and the probability that both will survive is 0.9838. A manufacturer of exercise equipment knows that 10% of their products are defective. They also know that only 30% of their customers will actually use the equipment in the first year after it is purchased. If there is a 1-year warranty on the equipment, what proportion of customers will actually make a valid warranty claim? So we assume that the defectiveness of the equipment is independent of the use of the equipment. So the probability that it's defective and used is going to equal the probability that it's defective times the probability that it's used. So again, the probability that it was defective is up here. It's 10%. We change that to a decimal to get 0.10. And then we have the 30% for the used, and we change that to a decimal, and that's how we got 0.30. Again, since they're independent, we're multiplying them together, and there's your total probability on the bottom, 0.03. So it doesn't matter how many independent events that you have. So we've been just doing with 2 events, but you can have more than 2 events. So you can have 3 events, you'd multiply 3 probabilities together. You could have 4 events, you can multiply 4 probabilities together. So the probability that you have all these independent events is going to equal the probability of the first event times the probability of the second event, so on and so forth until you get up to the probability of your last event. And again, we're just multiplying them all together. So here's going to be an example that's going to deal with more than two things happening at the same time. We're going to go back to our females surviving. The probability that a randomly selected female aged 60 years old will survive the year is 99.186%, according to the National Vital Statistics Report. What is the probability that 4 randomly selected 60-year-old females will survive the year? So again, we want the probability that all 4 will survive. So what we really want is the probability that the first survives, and the second survives, and the third survives, and the fourth survives. Again, one surviving in no way, shape, or form is going to affect whether another one lives or dies. So we're going to take those probabilities and we're going to multiply them together. Again, the probability for any one woman over the age of 60 to survive is 99.186%. So we're just going to change that to a decimal again and multiply it by itself 4 times. And in the end, that answer will give us 0.9678. Changing it up a little bit, the probability that a randomly selected 24-year-old male will survive is 0.9986, according to the National Vital Statistics Report. What is the probability that 20 randomly selected 24-year-old males will survive the year? Again, independent events. One male surviving and no way, shape, or form is going to affect any of the other ones surviving. So they're all going to be independent events. So we want the probability that all 20 survive. So just like in that last example, we want the probability that the first survives, and the second survives, and the third survives, so on and so forth, up to the 20th person. So again, they're independent, so we're going to take those probabilities and multiply them together. So the probability that the first survives times the probability that the second survives times the probability that the third survives, so on and so forth. So we're taking that percentage of 0.9986 and multiplying it by itself 20 times. Now, I don't know about you, but I don't feel like sitting here and typing 0.9986 times 0.9986 20 different times into the calculator. So instead of multiplying it out 20 times, we can use exponents. So we can do 0.9986 to the 20th power, which would give us 0.9724 for our final answer. So the probability that all 20 survive is going to be 0.9724. So that's the end of objective 2. The next video will deal with objective 3.